to be the complex numbers, just to kind of think about this very concretely. And let's fix one particular group. That's the group SLN. So these are n by n matrices with complex entries. Now SL is, by the way, is a very interesting group, even if you feed this some other object. So for example, SL over a ring is very interesting, right? So we learned in Young-Mi Her's beautiful talk last week about invariant, about the use of Quillen-Suslin theorem and the study of wavelets and the context of the Quillen-Suslin theorem. So let me tell you what was the main result in Young-Ju Park's dissertation. Okay, so if you take, as a sideline, if you take SL of the polynomial ring, you take the special linear groups, these are matrices with entries in a polynomial ring over a field with polynomial entries with determinant 1, so invertible polynomial matrices. And let's say the matrix size is at least 3. Okay? Then there's a Suslin's stability theorem that says every matrix like this can be factored as a product of elementary matrices. So an elementary matrix is a unit matrix, identity matrix, with one off-diagonal entry. So those always generate a subgroup of SL for any ring. But the amazing thing for a polynomial ring, and matrices of size at least 3, the converse is true. And Young-Ju Park gave an algorithm to find such a factorization. So that's an extension of the Quillen-Suslin algorithm that some of you saw in the exercise on Friday. But no such difficult thing today. Today we'll just take n by n matrices with field entries, and they have determinant 1. Now by a representation I will mean a group homomorphism from that group into some other space of matrices, so GLV, where V is some other complex vector space. And today all my homomorphisms will be polynomial homomorphisms. So this is a map that's a polynomial map. Okay? So let's say V, just to be very concrete, so let's say V is an m-dimensional vector space. So, and let's say m is bigger than n, right? So then I have a polynomial map that eats small matrices and makes big matrices. So to specify rho, I have to tell you a list of m squared polynomials in n unknowns, and then I can arrange them to be homogeneous of the same degree. That's because of this hypothesis. Okay, so that's the data. Now again, we have an invariant ring. So now the ring of invariant ring is the polynomial functions in m variables, the polynomial functions on V, well, that are invariant. So rho of pi applied to f is equal to f for all elements pi in SLN. Okay, so these are all polynomials upstairs that are left invariants by big matrices under this representation. So this is the invariant ring we're going to be interested in. Now here's a very important fact. G is a reductive group. i.e., for this group and any polynomial representation of that group, a Reynolds operator exists. I'm not going to write down the Reynolds operator for you. There are different ways of writing it. I'm just going to sort of talk a little bit of philosophy about the Reynolds operator. So for SLN, there exists a Reynolds operator. And therefore, by we said, invariant rings are finally generated, right? It's the same proof. Okay? Now this is actually very, very interesting. So there are different ways to think about this. So one way to think about this is the sum that we had for the finite group can be replaced by an integral, right? So most of us love calculus, and therefore we love replacing sums by integrals, and that's what you can do. So you can actually replace the sum by an integral. You can't quite integrate over this group. You cannot quite integrate over this set, so you go to what's called a maximally compact subgroup, and that's the standard story. So the way this is usually presented nowadays is you go to a maximal SUN, some compact subgroup. That's a thing you can integrate over, and then the sum becomes an integral. Okay, that's how it's taught nowadays. Okay, because we all took calculus. Back in the times of Hilbert, that was not the way people thought about it. Right? In fact, this theorem was known long before 1890. In fact, Cayley had an argument for that. So there's something called the Cayley omega process, which is a differential process. So you can realize the Reynolds operator either as an integral operator over SU or as a certain differential operator. Okay? And anyway, so this, which I like a little better. I prefer the differential operator. It's more algebraic, less analytic. And there are different ways of realizing this. But the point is sort of interesting historically that this fact was well known by the time of Hilbert, but the shocking news was the ideal of the concept of an ideal, and that the ideal is finally generated. That was the shocking news. Okay. Okay, let's do an example. The adjoint representation. So my example 1 is the adjoint representation of SLN. Okay. What's V? Well, V is now the space of n by n matrices. Okay, so M is n squared. Okay? So that's the adjoint representation. Now, whatever the adjoint representation is, if you paid attention, you will know that this representation is given by a list of n to the 4 polynomials in n squared variables, to be revealed now. So what's the action? Right? So let me say it. The action rho is by conjugation. Okay, so you have a matrix, right? And you multiply on one side by pi and by pi inverse on the other side, right? But since pi is an SLN, right, pi inverse is given by a polynomial. Is that clear? Right? So pi inverse is a polynomial function of pi. Polynomial of degree n minus 1 in each coordinate, called the adjoint. Okay? So is that clear? Yeah. So therefore, this action is a polynomial representation. Okay? Let me tell you the answer. So the ring of invariance is generated, it's a polynomial ring generated by the coefficients of the characteristic polynomial. Okay, so each coefficient, so here if you have an n by n matrix, you can form its characteristic polynomial, right? That characteristic polynomial has a bunch of coefficients, right? So it starts maybe with the trace, and then something, it ends with the determinant, right? So the trace and the determinant and other things in the middle, and they are obviously invariant under conjugation, and the claim is that every other invariant, if Bo comes along with any other invariant under conjugation, then that's a polynomial, in this example uniquely in terms of the coefficient, the characteristic polynomial. It's always good, people sort of jump over this, but if you're not so familiar with the mechanics of this, it's always good to work out the representation. So for example, if n is 2, right, then I have SL2 acting on the 4-dimensional space of 2 by 2 matrices. Okay? So therefore, rho of an element of SL2, so this is an element of SL2, This will be a matrix of what size? This is a matrix, right? So row is a homomorphism. It eats a 2 by 2 matrix with determinant 1 and makes an element here. What's the size of this matrix? Abraham, what's the size of this matrix? 2 by 2. Frank, what's the size of this matrix? Okay. V is a vector space, so n is 2. So V is a 4-dimensional complex vector space. This vector space, like all vector spaces I have ever met, comes with a distinguished basis called E11, E12, E21, E22. So it's a 4-dimensional complex vector space with a distinguished basis. This is a linear transformation, endomorphism of that vector space. So it can be represented uniquely by a matrix of which size, Abraham? 4 by 4, right? Because every endomorphism of a 4-dimensional vector space with the distinguished basis is uniquely written as a 4 by 4 matrix. So let's fill that 4 by 4 matrix. Each of these entries is a polynomial in A, B, C, D. I have told you in an indirect way what those polynomials are, but it will take a little practice to unravel what these polynomials are. Well, should we try a couple entries together? So for example, what would be first thing, let's write down the names of the basis vectors. If you have an endomorphism of a vector space, it's always good, and Macaulay does that for you, to write down, so the names of the basis vectors are 1, 1, 1, 2, 2, 1, 2, 2, and then 1, 1, 1, 2, 2, 1, 2, 2, right? So where 1, 1 is the basis vector, that's this matrix. And 1, 2, is the basis vector of this matrix, and so on. So that's the distinguished basis. So, I always get accused of choosing bases or endowing spaces with bases, but came to me, right? I mean, this basis came to me. Okay, so that's my basis. So the columns here. So the columns of a matrix are the images of the first basis vector. So if I apply, this linear transformation to this element, I can fill this basis. So we do that. So now comes the hard part, right? So I did this for you. So we need to calculate the image of this basis matrix under this endomorphism. And how does the endomorphism go? It's an action by conjugation. So let's do conjugation. A, B, C, D, 1, 0, 0, 0, A, B, C, D, inverse. Okay. So how do you, I forgot, you swap these and something like that, right? So now it gets hard, okay? So far now comes the hard part. So you go D, A, minus B, minus D. Minus B, C. Okay, well, so let's copy that. D minus B minus C, A, okay? Divide by the determinant. Done. Okay. Okay. Now. Okay. Now we multiply. Okay. So let's do the one on the left first. Okay. So that fixes this and makes it 0 here. You agree? We get rid of this. Let's It's not so bad, you know. Now we go AD wait a second. CD minus AB. You guys are so fast. Sorry for being slow. Minus BC. Okay? Okay. Now we have an element in our vector space, V. Now we have to decompose this into the basis. Right? So this is evidently AD times E11 minus AB times E12 plus CD times E21 minus BC times E22. Now those are the columns. This is the entries in the first column. And I think I'm off here. Okay, that's a plus. Okay. So that's how you fill the matrix. So that's how you fill the matrix for the adjoint representation and any other polynomial representation of SLN or products of SLNs. Let me torture a few more people. What's the determinant of this 4x4 matrix?
These?
Yeah, we just filled a 4x4 matrix. In your opinion, what's the determinant? Oh, if you fill the rest, you know, you calculate the determinant, it equals. Anybody have an opinion? Zero? Can't be zero, right? Because these have non-zero determinant. One? Huh? It's a homomorphism. It's a trick question. Okay, the determinant will be 1, right? Because it's a polynomial representation of SLN. Okay, so I like you to do this for many represent. Whenever you see symmetry, when anybody speaks to you about tensors, as you study the Landsberg book, I want you to actually write out rho explicitly. Okay, and once you've written out rho, I want you to check that the determinant is a power, that the determinant of the big matrix is the power of the determinant of the little matrix, which in this case happens to be 1. Now the ring of invariance, as I said, is in this example generated by the trace and the determinant of a 2x2 matrix. So this is the subalgebra of the polynomial ring in x11, x12, x21, and x22, right? And the ring of invariance under this action is generated by this polynomial. So this polynomial is x11 plus x22, and this polynomial, which is x11 times x22 minus x12 times x21. I'm going to rewrite the generators a little bit. I can also write this as the trace of x, and I can use, instead of the determinant, I can use the trace of x squared. I like that a little bit better. Okay, so I can take traces of powers of x. How about, very important problem, how about simultaneous conjugation of several matrices? Okay. So now V is not the space of n by n matrices, but it's several copies of this. So it's this thing, direct sum, this thing, direct sum, this thing. So maybe R times. So I have R n by n matrices, and I act on this by simultaneously conjugating them all. This comes up in lots and lots and lots of applications, including algebraic statistics, actually. So this comes up in many applications. The ring of invariance is generated by traces of words. So now I have several matrices, x, y, z, and I act by conjugating them all. Now I take any word like x squared, y, z, x, y squared, z, x, right? Any product of these matrices, I take the trace. And that will be an invariant. And it's a well-known theorem that these traces generate the ring of invariance. But it's an active area of research as to how far you have to go and what are the relations on these traces. Very, very important problem. Let's do one more example, since we talked quite a bit about the Grassmannian in our NIMS program and in this class. We talked about the classical Grassmannian. We talked about the tropical Grassmannian. Yesterday at lunchtime, we even talked about the Grassmannian over a finite field. So the Grassmannian is everywhere. So let's see how the Grassmannian comes out of these invariants. So let's take V to be Cn, direct sum Cn, blah, 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 direct sum Cn, and rho is the action by left multiplication. Let's say I have S copies, so it's left multiplication on n by S matrices. And let me assume that S is bigger than n to make it interesting, okay? Right, so I have the n times S dimensional vector space of rectangular matrices, and they look like this. That's a rectangular matrix. And here on the left, I can act by invertible n by n matrices of determinant 1. Then I get another matrix, okay? I have told you rho. All of you, including Matt, knows how to write down an n times s, an ns times ns matrix that realizes this representation. Strongly recommended to practice that if you haven't done it. Okay. So then, the ring of invariance is well known to be generated by the S choose n maximal minors. And this is sometimes called the first fundamental theorem of invariant theory, of classical invariance. Fundamental theorem of classical invariance. So this again, this goes way, way, way back early in the 19th century. People sort of knew that the maximal minors, generate the ring of invariance. Okay, so it's clear. So I have a matrix. So if I act on the left by an invertible matrix, right, then of determinant 1, then certainly the maximal minors here are left invariant by the matrix product formula. Right? For every maximal minor here, the determinant is the product of the determinants, but this determinant is 1, so this is left invariant. Okay, so by the determinant, these things are invariant, and you can show, for instance, by a Sogby argument, that they generate the ring of invariance, and this is the Plücker algebra. So this is the coordinate ring of the Grassmannian. That's the thing we tropicalized on Monday. Okay, for example, just to be very concrete, let's look at the case n equals 2, s equals 4. So again, I have my matrix A, B, C, D. It acts on the left by multiplication on the left on 2 by 4 matrices like this. And then, the ring of invariance is generated by 6 invariants, x1i times x2j minus x1j x2i, where I is less than j between 1 and 4. Now then, there's also the second fundamental theorem of an invariant theory. That tells you the relations, or, multiplicative syzygies among the generators. And in this case, we know what they are. So let's call these generators P12, P13, P14, P23, P24, P34, and then the relation is P12, P34 minus P13, P24 plus P14, P23. Okay? And there are many versions of this, this is Hermann-Weyl extended this, where you have several copies of the vector space Cn and a bunch of copies of the dual vector space. That's a very nice scenario, and this is all rather well understood. Okay, now I'd like to come to a harder example. In fact, the main example that Hilbert was interested in. So what Hilbert was mainly interested in, his contemporaries, were invariants of forms, where the vector space V that we're acting on is homogeneous polynomials of degree d in n variables. Okay. So we're interested. So now watch out. Right? We're looking at C of V. So we're looking at polynomial functions on V, where V itself consists of polynomials. So we're taking polynomials in the coefficients of polynomials that are left invariant under coordinate changes. Very, 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 very important topic.
Was it why this was important at the time?
Well, we wanted, so why is that so important? Why was it important? Why does it continue to be important? Well, let's talk about the word geometry and the adjective geometric. Okay? Well, this week in these super fast lectures, I'm giving you an introduction to invariant theory and representation theory. But add the adjective geometric, right? Then you get something called geometric invariant theory, and here you get something called geometric representation theory. These are important areas of mathematics. As a novice, as a student, you might think that the adjective geometric might make it easier. That's not true. It makes it harder. So geometric representation theory is actually harder than representation theory. Same with invariant theory. But what's geometry? Right? What is geometry? What are geometric properties? I give you a polynomial in x, y, z, and you look at this, you look at some property of, I draw you a curve. Right? So what is a property? Here you have a curve, and maybe here you have a curve, right? So they're convex, right? So that's a feature. That's somehow a geometric feature, that they're both convex, or that they're non-singular convex, things like that. So, and the insight that was sort of clear intuitively to people was a geometric property is one that's invariant. A property that's left invariant. So these are curves. These are hypersurfaces of degree d in n-1 dimensional projective space, right? And people sort of intuitively knew that to look for geometric properties of hypersurfaces or varieties in general, we should look for invariance. This was formalized, systematized in the famous lecture by Felix Klein. So in Germany, you have this olden days, right? You have the dissertation, and then you have a second dissertation called Habilitation, and then, finally you get this Habilitation, and then you start being a professor. And so Felix Klein started being a professor in Erlangen, and this very famous lecture he laid out the Erlanger program, where he systemized this point of view, that geometry is the study of invariance. Okay, I can go on forever. So all of these guys are great. When you read, Hilbert, Riemann, Schottky, Klepsch, they're all great. But Klein is in a class of himself. I mean, as a writer, as a philosopher, Klein is in a different league. He's really amazing. So, anyway. Please read Klein in German. Okay, so that's why invariants of forms are very important, because they capture geometric properties of homogeneous polynomials, that is to say hypersurface. So let's see some examples. Let's do quadratic forms. Okay. The situation is quite simple, but worth stating anyways. The invariant ring. So there's only one invariant, really, for a conic, for a quadratic form of a quadratic n-ary form. So this is the case d equals 2, is generated by a single polynomial, and that's the discriminant. Okay, so a quadratic form is given, let's do this example, n equals 2, right? So V is a three-dimensional vector space consisting of binary quadratic forms, which I write like this. So this is the three-dimensional vector space that comes with a distinguished basis, x squared, xy, y squared. Okay. We all know how to write rho. We clear on writing rho, right? So we have a representation. If you have a 2 by 2 matrix with determinant 1, it's called A, B, C, D. You can now write down a 3 by 3 matrix whose entries are quadratics and A, B, C, D that acts on this three-dimensional vector space, and the rows of this 3 by 3 matrix are labeled x squared, xy, y squared, and the columns of that matrix are labeled x squared, xy, y squared. Okay? So that's our action. And the ring of invariance, so interested in polynomials in U1, U2, U3. And that's generated by a polynomial U1 squared minus 4 U0, U2. And as I jokingly said before, you see this polynomial in Germany in middle school, in China in elementary school. So that's why it's an important polynomial, because it's the unique invariant. Okay? Every other invariant is a polynomial function in that particular invariant. Okay? That generates the ring of invariance. Now, yes, question.
Geometric. So if I have two polynomials and they have the same invariance, then there is an element of SLN that will. Is that the true statement?
Okay. Let me repeat the statement, and then we'll discuss whether it's true. Okay. So we said earlier, in the case of rotations by 90 degrees, that the invariant ring is the coordinate ring of the quotient space. So that the set of orbits forms a variety, namely the zero set of some polynomial in A, B, and C. Okay? For infinite groups, it's not quite true. It's not quite true. It's true in a dense open set. And you can see this here. So it's true if your quadratic form, if your symmetric matrix is invertible. Right? So if you have an n by n symmetric matrix over an algebraically closed field, if it's invertible, then you can move one to the other by SLN if and only if they have the same discriminant. But there are other orbits, namely lower rank strata, and some people study them, So lower rank strata you cannot capture by these invariants. Okay? That's not a flaw of invariant theory, that's a feature of invariant theory. And invariant theory, particularly geometric invariant theory, addresses that issue. Okay? So, but the first approximation, it's true. The ring of invariance is the coordinate ring of the quotient space, to the extent that the quotient space is a variety. In general, I actually had this sentence here. C, the invariant ring, is the coordinate ring of a certain variety which I call V//G. Okay? Now, first of all, why is it the coordinate ring of a variety at all? Well, because it's Noetherian, right? It's finally generated. I proved it to you, modulo the Reynolds operator. I proved to you that this is a finitely generated algebra. It's a graded algebra, so it is the coordinate ring of some space, the homogeneous coordinate ring of some space, called proj of that ring. And that space has this funny name, okay? V//G. So this is the orbit space, which is, that thing, but it's not exactly the same. It's more or less the orbit space, but you have sort of degenerate orbits that you have to be careful about, okay? Now this quotient space encodes geometric properties, as we learned from Klein, right? So encodes geometric properties of hypersurfaces of degree d in Pn-1. And that's more or less the definition of geometric property. Let's talk about the first non-trivial example. So d equals n equals 3. Okay, so this is the space of ternary cubics. So V is a 10-dimensional complex vector space. So this is the space of ternary cubics. Okay, it's a vector space with a distinguished basis called x cubed, x squared, y, blah, 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 z cubed. At 1:30, we're going to do a little optimization problem on that space. Some of us will do a little optimization problem on that space. Okay? 10-dimensional space. Let me call the coordinates actually A300, A210, and so on. Okay? So okay. The space of symmetric 3 by 3 by 3 tensors. Okay, well, what's geometric about it, right? These are cubic curves in the plane, right? So there's pictures that look like this, right? And on Friday, if you speak Korean, you can listen to a lecture in the NIMS school on elliptic curve cryptography, but I think it's in Korean. Okay, so these are elliptic curves in the plane, cubic curves in the plane. Here's a theorem. The ring of invariance, CVG. The ring of all polynomial functions in 10 variables, A300, these are the variables, right? So the unknowns are the A's. So I have a polynomial ring and 10 unknowns, and I act by 3 matrices with determinant 1 on that polynomial ring in 10 variables. And you, young man, better write out the 10 by 10 matrix for that row. Highly recommended. Okay? Okay, that's generated by two polynomials, S and T. S and T are the fundamental invariants where the degree of S is 4 and the degree of T is equal to 6. Okay, so there is a certain polynomial, and up to scaling these are unique. There's a unique homogeneous invariant of degree 4, so it's a polynomial of degree 4 in these A's, I'm going to call S, and there's another polynomial of degree 6 in these A's that I'm going to call T, and they generate the ring. Every other invariant polynomial is uniquely, in this case, a polynomial in these two. Okay? So these things, they have names. Okay? So this one, for example, is called the Aronhold invariant. That's a certain polynomial with 26 terms, and this guy t has 103 terms. So let me give you one. So one of these terms looks like A300 squared, A030 squared, A003 squared. Okay? So on the homework, on the exercise, I think I'm asking you to produce an invariant of something, you know. So how do you actually produce invariants? Well, first of all, you want polynomials of the right degree in the A's. So let's think about all the monomials of degree 6 in 10 variables. There's a lot of monomials of degree 6 and 10 variables. Most of them are irrelevant. The only ones that we're going to care about are symmetric as far as the weights is concerned. We're only going to be interested in invariance that has weight 6, 6, 6. So by that I mean if you add the indices as vectors, you get something that, you know, 300 plus 300 plus 030 plus 030 plus 003 plus 003 is this. And that's true for every other term. Every monomial that is allowed to appear in invariant has to have that property. Why is that? Well, that's because if you are SL3 invariant, in particular you're invariant on the diagonal matrices. So you're invariant on the diagonal matrices of determinant 1. And that means that every term has to be like that by the calculation that I referred to Abraham an hour ago. Okay? It's torus invariant. Okay? So therefore, you don't have to list 1 trillion terms. You only have to list 103 monomials. There are only 103 monomials in the picture. And then you zip off the coefficients by a little linear algebra calculation. Okay? It's actually very easy to make these invariants. Okay? Of course, you can also go to the web, you know, and download them. But then there's always a scaling. You know, the other guy always has another multinomial coefficient that's different from yours. You know, it's usually faster you make the invariant yourself rather than download it from the internet. Okay? And this guy has only 26 terms. So the Aronhold invariant, well, that's sort of important for tensors, right? So the Aronhold invariant vanishes if and only if the tensor has rank at most 3. So when I assigned the question on Friday, Luke came up with this brilliant representation of x, y, z in rank 4. I knew it doesn't have rank 3 because I plugged it into the Aronhold invariant. It didn't get 0. Okay? So the Aronhold invariant didn't vanish, so I knew that the rank was bigger than 3. And that's S. So S of, you know, S of 0, 0, 0, 0, 0, 1, 0, 0, 0 is not 0. So therefore, the rank is at least 4. Okay? That's how it works. There's the discriminant of a ternary cubic that's an invariant of degree 12. That's t squared minus 64 s cubed. Right? Every invariant, including the discriminant, is a polynomial in S and T. So that's the discriminant. The J invariant is very important. That's a rational function. It's an invariant rational function. So J is S cubed mod delta. And that's very important because this is actually, you know, quotient of rational functions of homogeneous polynomials of the same degree. And that generates the field, the function field of V//G, which by definition is proj of this invariant ring. And so this is sort of the moduli space of these objects, of plane cubic curves. Okay? Now you can study other, you know, moduli spaces. So 2 examples that are nice to study are plane quartics. So that would be the case d equals 4 and n equals 3. These are plane quartic curves. There's a finite list of invariants on the web. It's big. Remember, that was Emmy Noether's thesis problem that she didn't complete, but in the meantime, with some computer power, it was essentially by Igusa. Was basically, he mostly did most of the work, and then some finishing touches in the 80s and 90s. So there's a list now. The corresponding proj in this example is more or less, I'm lying a little bit, is more or less, it's not quite the same, but it's more or less, not quite true, but almost a certain space called M3 bar. It's a 6-dimensional space of genus 3 curves in the plane. I'm missing a little bit of stuff, but you can get that stuff by looking at binary octets, which is D equals 8 and N equals 2, and that captures the hyperelliptic part that's missing. Okay? So for every value of D and N, there's a beautiful and deep story intimately related to the lecture we will enjoy on Friday tomorrow at 2 p.m. Any questions? Okay, let me give you the answer to Hilbert's question. So that's Hilbert's fourteenth problem. Well, Hilbert showed that if the group is reductive, the invariant ring is finally generated. But not every group is reductive. Not every group is reductive. And it was an open problem. It remained an open problem for some time whether the invariant ring is always finally generated, regardless of whether the group is reductive or not. And this was solved by Nagata. Solution. And the answer is no. Okay? So Nagata gave a counterexample. I think it was 1959. So many, many years, 60 years, 70 years after Hilbert's work, a counterexample was found. I'm going to describe it to you. And you can reboot. So if you were a little lost, all this M stuff, you can reboot. So think about rotations in the plane by 90 degrees. You're already done homework number 1. Okay, so we want to cook up a matrix group. We want to make a group of matrices that acts on a polynomial ring, and the ring of invariance is not finally generated. And I'm going to give it to you explicitly right now. I'm going to give you the matrices. You ready? Okay. So first of all, what's the group? So let's start with the additive group. K to the n. Okay? Well, K to the n is a vector space, so in particular it's a group with respect to addition. That's a group, okay? Now, it's not reductive. I'm going to give you a matrix representation in a moment that's not reductive, so it's known to be not reductive, and I'm going to give you the action. I'm going to make it act on a vector space of dimension 2n. So I'm going to represent this by 2n by 2n matrices. And just to save time, I'm going to make it act on the polynomial ring right away. So I'm going to act on a polynomial ring in 2n variables, x1 up to xn, y1 up to yn, via a rule that you can translate into matrices. Okay? And the rule is pretty simple. On the x part, you do nothing. xi gets mapped to xi. Pretty boring, okay? And then yi gets mapped to vi times xi for every element v in that group. So v is a vector of length n, and vi is the ith coordinate. And I'm sorry, I wrote this wrong. This should be, I'm sorry, this should be yi plus vi xi for v in the group in k to the n. Okay, so this is a linear action, right? So for every vector v, maybe for every vector v, we can write down an 2n by 2n matrix, that does this thing, right? It's basically the identity matrix, and then there's sort of another block, v1, v2 up to vn on the upper diagonal. Okay, very simple. But to make it interesting, let's make it a bit more interesting. Now let's going to fix a d by n matrix M, and let's take the vector subspace spanned by the rows of M. Okay, so G is the row space. And let's say, of rank D. So G is a d-dimensional vector subspace of k to the n, and that's a group also under addition. That's going to be my group. Okay, so I'm going to pick the matrix. So you're going to pick the matrix. So for every matrix M, there's a group G, the row space of G of M with respect to addition, with this action. Now what's the ring of invariance? I'm going to be interested in the ring of invariance. Well, let me tell you some invariants, just to get a feeling for this. So among the invariants are the following. Okay, here are some linear invariants. So I claim x1, x2 up to xn, they're invariant. That's pretty easy. Right? So they are invariant. Okay. Let me tell you some other invariants. And also, the d plus 1 times d plus 1 minors, the maximal minors of a certain matrix is pretty much like the fundamental theorem, So what you do is you take the diagonal matrix x1 up to xn on the left, and then you take on the right, take m here, and you add one more column, one more row, y1 divided by x1, y2 by x2, yn by xn. So one more row. So here you have d rows. So this is a matrix with d plus 1 rows. Now here you have some denominators, x1, x2 up to xn, but I'm killing these denominators. So every entry, is a polynomial. So every entry, so here I have the original matrix of constants multiplied with x's, and then I have the row, y1, y2, and so on, okay? So the maximal minors are invariants, and that's pretty much, because the same reason that the first fundamental theorem holds, because, well, if you look at this, so I take the y vector, and I multiply it, by a linear combination of the rows. So what I'm saying is, if I take a row of this matrix, I add it to the last row, then the maximal minors don't change. Not terribly difficult either. Is that clear? So I take a row, I have a matrix, right? I add a multiple of one row to another row, then the determinant doesn't change. Now sometimes they generate. So these suffice in some cases. Namely, if n minus d is at most 2, then they actually generate this ring of invariance. But not in general. Not in general. Okay, so let's make a table. It's d equals 2, n equals 5. So the difference should be at least 3, and this is the first interesting case. So then, we could look at 3, 6, 4, 7, 5, 8, 6, 9. Let's do that. Okay. So they don't quite generate, But in these cases, I can throw in, find a couple more generators, and here I can throw in a couple more. And there's a very explicit list. And the combinatorics that governs this list has the following names: D5, E6, E7, E8, and E9. Okay? So what are these things? Well, these are certain graphs known as Dinkin diagrams. So for example, the graph, it's a graph on D5 is a graph on 5 nodes that looks like this. Okay, and E6 is a graph on 6 nodes that looks like that, and E9, it sort of goes on like that. Okay, so those are the names of certain graphs. These graphs describe presentations of groups. And these groups are finite up to E8. And E9 is infinite. Okay? And, you check this. So it turns out that here, in this case, for this case, it's not finitely generated when M is a general matrix. Okay, so M is a general matrix. Think about the Gale dual of M. So M is really the orthogonal complement is given by a 3×9 matrix. So it's given by 9 points in the plane. Right? So M specifies the relations among 5 points in the plane, 6 points in the plane, 7 points, 8 points, 9 points in the plane. But if you take 9 points in the plane, you write down their relations, you do this action, then you get an algebra of invariance that's not finally generated. I will not tell you the reason why, but I told you the action. I told you the matrices. So I told you a group of 18×18 matrices very explicitly whose invariant ring is not finally generated, but the reason involves some algebraic geometry, which I'll be happy to discuss over lunch. There will be one more part to this lecture. Let's take another 4-minute break. Then I'll lecture for another 11 minutes. It's just like in soccer, okay?